Hello and welcome. This presentation is going to explain what the IL2RG gene is and how its mutations affect humans. I'm Emma McClure, and my partner, who will appear later in the video, is McClurePerndreca. Without further ado, let's begin the presentation. I will begin by explaining the basics of our protein. IL2RG stands for interleukin-2 receptor gamma chain, which means it's the gamma segment of a glycoprotein that helps regulate the immune system. The entire gene, as pictured on this slide, is actually much larger than what we'll be showing today. The highlighted portions on this picture show the subchain A, which is the first of 38 other subchains. We selected only this chain to show because it's a hotspot for mutations, as well as the binding site for enzymes, so if anything goes wrong with this segment, it often affects the entire gene. But what does this gene specifically do? Before we get into this, I should explain the basics of the immune system. The immune system is a network in your body that tries to eliminate possible causes of infection and other illnesses. A lymphocyte is a type of white blood cell that is part of the immune system. The main type of lymphocytes that IL2RG affects are NK, natural killer cells, which specifically eliminate bacteria, viruses, and malfunctioning cells. However, IL2RG is also related to T and B cells. All of these cells allow a human to be able to fight off illnesses and have a healthy body. In summary, your body produces lymphocytes to defend against possible causes of illnesses. These lymphocytes are produced in bone marrow. The bone marrow cells contain receptors in their membranes that allow them to transmit and detect signals from other cells. When the body needs more lymphocytes produced, certain signals are sent to the bone marrow cells that make them start producing lymphocytes. Information in IL2RG creates a receptor on bone marrow cells, which produce blood and more specifically white blood cells. The transmitted signals we mentioned before are detected and realized by this receptor. This receptor needs to be able to function properly in order to detect the signals to produce the lymphocytes. Mutations that prevent enzymes from bonding to it or don't allow it to function otherwise will eventually lead to a decreased amount of T and B cells. It also often leads to no production of NK cells at all, which is harmful to the human.
When there are mutations in the IL2RG gene, like the methionine deletion we chose to focus on for our project, the IL2RG becomes unable to communicate by not being able to bind properly to phosphoroproteins, so then it cannot carry out the instructions for the creation and production of natural killer cells, which compromises the immune system of a person affected with a mutation and puts them at a higher risk for infections and even cancer. As I mentioned earlier, a person becomes compromised when they can't produce natural killer cells because of a mutation on the IL2RG gene. When this happens, it can either be severe combined immunodeficiency, SCID, or common variable immunodeficiency, CVID. And this is where there's normal amounts of B and T cells, but no or reduced amounts of natural killer cells. There was a specific case of a boy and his grandfather where they both had this affliction and they both didn't have natural killer cells. And the grandson had ear, airway, and gastric inflammation, chickenpox, with no response to vaccines, while the grandfather had gastrointestinal tract infections, flu and strep, type 1 diabetes, and celiac disease. Both of these patients were treated with immunoglobulin substitution therapy, which is essentially where antibodies are given to the patients through plasma of other people with functioning immune systems.
This is our physical model, and it took 4 hours and 47 minutes to print. We chose to highlight the alpha helices in red, like shown here, and the beta pleated sheets in blue. We chose to color the struts black so they've blended into the background more and didn't take away from the rest of the model. And we highlighted our mutation, methionine number 23, in yellow to make it more clear to the person viewing the model.
Looking at this protein and even other proteins is really helpful because when you can look at the structure like that and see how it interacts with the proteins it binds to, you can really understand how it works, and you can even look at how mutations like insertions or deletions would change the interaction. And if you can understand like that, then you can come up with better specific treatments that are more effective and efficient and can save lives, like in the case of the boy and the grandfather.